Let's have a look at cubic curves. Now, cubic curves just have the highest power of x being x cubed. The most basic cubic curve that you can get is just y equals x cubed, but in a moment we'll have a look at some that are more complicated. Now, this is the basic shape of this curve. It starts down low and it goes to high, and you'll see that it's completely in either this quadrant down here or this one up here. Now, that makes sense if you consider that if x is positive and we take a positive number and cube it, the answer will also be positive. Whereas if x is negative, if we cube a negative number, then we'll get a negative number. So that explains why we never get any of this graph in these two quadrants. It's always here or here. Now, we could also graph y equals negative x cubed on the same axes, and just as x cubed sits in these two quadrants, negative x cubed sits in the other two. Because of course, if x is a positive number and we cube it, we'll get a positive number, but if we then whack a negative out the front, it will be negative. So anytime x moves this way, we've got negative values of y. And when x is negative, y will be positive. So what we get for this curve is it looks identical, but it's as though it's been flipped around either this axis or that one, whichever one you like, but it goes in the other two quadrants. So that's y equals negative x cubed. And all negative cubic curves generally go from high to low, whereas the positive ones go from low to high. Now, one thing that all cubic curves have is one point of inflection. Now, we haven't really discussed these yet, so let's have a good look at them. A point of inflection is just a place on the curve where the concavity changes. So if you can think of a concave surface as being one that's like a bowl, can hold water, and a convex surface as being the opposite, well, those words are handy, but mostly in maths we talk about something being concave up, like a bowl, or concave down, like an upside down bowl. So on a positive cubic curve, you can see that the first section of the curve is actually concave down. See that section there? It looks like an upside down bowl or an upside down cup. Whereas the second section is concave up. And the point where the concavity changes is right here at the origin. Now, this curve and this curve both have special points of inflection that are actually also flat spots. So we call these horizontal points of inflection because there's actually a small, just a very short flat spot there as the concavity changes. Not all cubic curves have a flat one, but they all have a point of inflection of some sort. And you can see here that the negative cubic curve starts off concave up, but then it changes to being concave down. Now, two ways that you can spot a change in concavity if you're not completely sure. I mean, you can just look for sections that look like they hold water or they don't. But another way you can do it is if you run your pen along the curve, you'll see that as I run along it this way, trying to echo what the curve's doing, my pen is actually turning clockwise. And yet when I get to the point of inflection, it starts turning anti-clockwise. So that's a giveaway that you've passed a point of inflection when it starts turning the other way. The other thing you can do is note when your pen is actually crossing the curve itself. So if I run my pen along the curve here, I can see that the pen is straight, whereas the curve is curvy, obviously. So technically it's sort of sitting, on one side of that curve, whereas when it gets to the actual point of inflection, it sits so that the curve's sitting out one side of the pen on one side and one side of the pen on the other side. So it's actually, my pen is crossing the curve itself. That's another way that you can spot them. But with a bit of practice, you'll spot these quite easily. So we know what y equals x cubed looks like and negative x cubed. If we have a number out the front of our x cubed, but none of this, then that number will basically just stretch our cubic curve. It'll have the same basic shape, but it might be sort of fatter or skinnier. But once we have more terms, it really increases the complexity of the curve. So any terms at all in x squared or x or some other numbers are just going to change the nature of it. Now, these more complex curves still have one point of inflection, but all of these extra terms basically mean that the point of inflection won't be a horizontal one. So they generally are shaped like this, and they'll still have a section with concavity down and concavity up, but here you'll notice the point of inflection is somewhere around about here, and it's not actually a flat spot. Or sometimes they're actually a lot more wobbly than that. Again, you'll notice that a curve shaped like this has a concave down section and a concave up section and a point of inflection, which would be right where the two are changing, but it ends up looking wobbly. Now, which way generally does it go? Well, if this A is positive, then we're going from low to high, just like our y equals x cubed curve does. But if A is a negative number, then we're going to have a shape that goes from high to low. and that means it will be shaped generally like this, or perhaps more gently like that. So a variety of shapes can come along. Now, at this stage, we can only graph these more complex ones if we get them in factored form. So you'll generally be given them like that, because also we haven't learnt a method for factorising these unless they can be done in two pairs, and they rarely can. So if you get a curve that's in this form, where A is just a constant, that's this number that's out the front, which tells us if it's going from low to high or high to low, and then a bunch of things in brackets, where each time we've got x minus alpha, x minus beta, x minus gamma. Now this is a symbol you might not have seen before. It looks a little bit like a Y, but it's not a Y. I sort of draw it curvy and then around like that. And that's just the third letter of the Greek alphabet, so it makes sense after alpha and beta to use that. Where alpha, beta, and gamma are the x-intercepts, or the roots, well, then we can graph it. And the reason we can graph it is because we can nail down something of where it sits in space. So let's have a look at an example to see how to do that. Okay, so let's graph this one. Now, it's a cubic curve, and we can tell because if we multiplied it out, which we don't want to do, by the way, but if we did, then the biggest power of x would be x cubed. And I think you can appreciate here that if we did multiply this out, we'd get all sorts of other x squareds and other x's and other numbers. As it is, though, we can use our method of finding intercepts to graph this. So let's start with the easier one, find the y-intercept. So when we find the y-intercept, we're basically letting x equal 0. So when you let x equal 0, you're just going to have a 0 here. So this section will be 1 multiplied by, well, let's start with 2, multiplied by 1, that's 2, multiplied by -1, that's -2, and -2 multiplied by -4 is going to give us +8. So the y-intercept is up here at 8. You can jot that down if you want. Now to find x-intercepts, if we let y equal 0, now I'm just going to write that down and look at it. I don't want to rewrite the whole thing. I can almost just cover that up and imagine it's a 0. Now how could it be a 0? Well, if you're multiplying a bunch of things together and you're getting 0, one of them must be 0. Now this 2 is sitting here going, don't look at me, I can't be 0, I can only be 2. The only parts that could be 0 is this part, and this part. So how do you make this part equal 0? Well, x would have to be -1 for that to happen. So we've got x equals -1. For this part to be 0, x would be 1. And for this part to equal 0, you'd have to have x being 4. So that's quite straightforward and easy to get from the graph just by, to get from the equation just by looking for intercepts. So now, when we're looking for intercepts, we've got one here at -1, one at 1, and one at 4. So we've got 4 points on the graph, and that's enough really to just start graphing, because we know that the basic shape, it's a positive one. It's going from low, it's doing a wobble, and then it's going high again. So it must go through here from low, coming up to this point, down again, and then up again. Now, I don't know how low this dip is. I don't even know if it went up a little higher, perhaps on one side here or the other, but this is enough for now, and mathematically this would give me full marks, and I just label the intercept, and I've got my y-intercept up there, and I've done it. Now, it's important to notice that even though these two intercepts are equidistant from the origin, that doesn't mean that this high point is necessarily equally between them. This is not a parabola. It's going to have a wonky shape. Right, let's go again. Now this one, first thing I'm spotting is which way up it is. It's a -1, and that means it's generally going from high to low. Now let's do things the other way around this time, just to mix it up. To find the x-intercepts, I can see that x would need to be -2, 3, or 4. So I can go ahead and plot those. To find the y-intercept, I need to let x equal 0. So that means I'd have a negative, so -1 times 2, that's -2, times -3, that's 6, times -4, so I've got -24. Now you don't have to have the same axis on your, you don't have to have the same scale on your x and y axis. So if I want to put my -24 just down here, it doesn't matter if it's not sort of, in the same scale, because mathematically that's enough to show where it goes. Now I know the basic shape, it's going from high to low, so it must come up, it must sort of do a little hook here, and then it comes through somewhere like that. Now I can't be sure, it might go down lower before going through that point, or it might go through that point and then go low. It might even come up high here. But mathematically, this is all I need on my graph to get full marks. because the X-intercepts are correct, the Y-intercept is correct and it's labelled, and it's got the right basic shape. Now, I've referred to the X-intercepts before as roots, and that's just another word you can use when describing them. But a double root occurs where the curve only just touches the x-axis instead of going all the way through it. And to find these, you look for the squared factors. Now, I think this is easy to remember because that feature of something being squared, to me, that is a little bit reminiscent of a parabola. Now, it's not a parabola. This can be part of any curve. In this case, it's still a cubic curve. And we can see that if we look at this example, because if we were to expand this out, this section right here will give us x squared as the highest power of x, but then we've still got to multiply by another x. So our whole expansion would have the highest power of x being x cubed. But this section is a little bit special. It's not a parabola, but it's reminiscent of one, and that reminds me that when it gets to this point here, it's just going to actually just touch. So if we use our method that we've already got of finding our x-intercepts, I can see that if I let y equal 0 to find it, x-intercepts, that will only happen if this section is 0, which happens when x is 1, or when this section equals 0, which happens when x is negative 2. But this one over here at negative 2 is a special one. It's a double root, and I can see that. Now, you could also write it out like this to appreciate that basically there's 2 intercepts at that point. Now, how can you have 2 intercepts? Well, it's a special one, okay? So to think through here, this is a positive cubic curve, which means it needs to go from low to high. So if it finishes high, there's only one thing it can do over here. It has to come up from this second intercept, which means that here it must just touch and be on the down low side like that and come up something like that. Now, working out what the y-intercept is something that you can do at the end if you want to. And again, your scale on the x and the y-axis can just be different to account for that. To find this point, I let x equal 0. So that means this section here is negative 1. So I've got 2 times negative 1 times 2, which is negative 4, times 2, which is negative 8. Now, you're setting out for that. If you want to actually set it out, you could say if x equals 0, y equals, and then you've got 2, negative 1, 2, 2, and a lot of people will find it easy to write that out just to make sure that they don't make a mistake. Now, to practice another one, let's change this question a little bit. What would we do if we'd had the squared part on the first section there? Well, in this case now, we'd still have the same 2 intercepts, but this would be the one that's the double root. So let's draw it up again. We've got our 1 and we've got our minus 2. Okay. And now we're going from low to high, but we know that we're going to have to go up through this one and come down and actually just touch this one. Now you'll notice that we're no longer going through that same intercept that we were before. And that makes sense because now if we're squaring this section, then when we sub in x equals 0, we've got negative 1 squared, which is just 1. So we end up with 2 times 1 times 2, and this point up here will now be 4 for this curve. Now again, we can't assume anything much about the rest of the shape, so just go in ahead and graph something generally curvy. This looks a little bit, I'm not happy with that. It looks like a V. It needs to be a little bit more U-shaped. So just make sure it's a nice curve. You can put arrows on the end, and that's all you need for your graph.